Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about continuous random variables. Our goal is to study uncertain quantities that can take continuous values, such as, for example, time, distance, weight, etc. We usually represent these quantities as real valued numbers. Our plan is going to be to define continuous random variables. Then we're going to introduce a tool that is very useful to manipulate these variables, which is the cumulative distribution function, and we're going to explain how it is connected to quantiles, such as the median that you might already have heard about. And then we will explain how to estimate both the cumulative distribution function and quantiles from data. The prerequisites for this material are probability, estimating probabilities from data, and discrete random variables. And in fact, let's start by reminding ourselves how we defined discrete random variables. We defined discrete random variables as functions from a sample space to a discrete set of possible values. And what we wanted is for the events that the discrete random variable was equal to each of these possible values, those events should be well defined and should have a certain probability assigned to them. Now, what we want to consider is whether we can do the same thing for continuous quantities. Okay, so here is a picture of how we defined discrete random variables. We have this sample space, omega, and the idea is that each point in omega is mapped to one of three values. Okay, so there's 2. I'm going to try to find roughly the same colors, 3, and 1. Okay, and the idea is that, now I'm going to use another color to show the actual function. So A, what it does is it maps each of the points in the sample space to one of these numbers. So all the points here are mapped to 1. All the points here are mapped to 2. Oops, wait. And all the points here are mapped to 3. So that's the function. Mathematically, the discrete random variable is a function that goes from the sample space to those 3 points. And every point is mapped to one of those points. And when we look at the probability that the random variable is equal to 1, then basically what do? We looked at the probability assigned by the probability measure to this green set of outcomes, which we call an event, this event. In this case, it has this probability. Okay, so this is represented by the probability mass function here. This is the PMF. The probability of the random variable being equal to 2 was the probability of all of these values in the sample space, and so on and so forth. So remember that this is just a mathematical definition. At the end of the day, we just assume that there exists this probability space, and we directly just define the random variable through its PMF. We don't really actually build a probability space and then represent the random variable as a function and so on and so forth. We never do this. Okay, we just define the PMF directly, because what do we care about? We care about the probability that the random variable is equal to each of its possible values. We don't care about the underlying probability space. It's important to have the underlying probability space because we need it to define the random variable rigorously, and in particular it's very useful to model dependencies between random variables, and we'll get to that. Okay, but it's also important not to get bogged down by the mathematical formalism. We need to always remember that when we think of discrete random variables, we think of them as uncertain quantities, and we care about the probability that the quantities are equal to each of their possible values, and for that, the probability mass function is more than enough. Okay, so sorry for this rant again about discrete random variables. I have a whole video just talking about that, but I thought it was important to remind ourselves of this before we dive into continuous random variables. Okay, so let's try to just do exactly the same thing that we did with discrete random variables with continuous random variables. So now I'm going to draw a small picture of what I mean by let's imagine that we have a sample space omega, and now we're going to define a random variable, let's say A, as mapping omega to some interval of the real line. Okay, maybe I'll draw a straight line so it looks prettier. Okay, so we're mapping to a certain interval of the real line. That means that, actually let me do that again. Okay, this is the interval of the real line. This is what we call I for interval. And now the random variable takes every point in omega and maps it to a different point in the interval. So just in the case of discrete random variables, we will never actually do this. We will never define the probability space and the function and so on. We're going to define other quantities that allow us to manipulate the continuous random variable directly. But first we need to figure out how we're defining it mathematically. Okay, so bear with me. The mathematical definition is also going to be a function from some probability, some sample space omega, in this case to real values. That is how we're going to define continuous random variables. But now we have to see if the same approach as with discrete random variables is going to work out, in the sense that can we just characterize the random variable in terms of the probability that it's equal to each of its possible values. Okay, so can I now just define the probability that A is equal to this particular value of the real line, the probability that it's equal to this other value, maybe B. So this is A, this is B. Can I just do that? Okay, can I just say, okay, there's this function from a sample space to the real line. Now I'm just going to worry about the probability that the random variable is equal to these possible values on an interval. Okay. Now we're asking, is this possible? We're going to see that there are some complications because of the fact that we're considering an interval which contains an uncountable number of points. Okay, so let's see, and essentially what we're going to see is that it's not possible to assign non-zero probabilities to all of the points in the interval, which is going to be problematic if we want to do exactly the same as we did with discrete random variables, where we characterize them through the probability that they're equal to each of their possible values. That's basically a summary of what we're going to do now. So now, we have this this interval, and now we are asking, let's say that we assign non-zero probability to many points within the interval. In fact, we're going to try to assign non-zero probability to all of the points of the interval. And now let's see what happens. So I'm calling S the points within the interval that have a probability that is non-zero. Okay, I say, oh, this random variable A is mapping onto this interval, so I'm going to define the probability that A is equal to 2.3, to 3.75, and so on and so forth. Okay? Now let me ask you, what is the probability, if I sum all of these probabilities of all the points in this set, which are the points such that the probability that A is equal to that point is non-zero, what should be the sum of all those probabilities? And for that, maybe we can remember what we did for discrete random variables. I'll go back for a moment, and maybe I'll erase all of this so that you can see a little bit better. So for discrete random variables, we saw that because each of these points only maps to one of the discrete values, and all of these sets are disjoint because this point cannot map to 2 1 to 1 at the same time, these sets that we have defined here, these events that map to each of the possible values, they're a partition. So when we add up their probabilities, the probabilities must add up to the probability of the whole sample space, which is equal to 1, okay, because they are disjoint and they cover the whole sample space, and we know that the sample space has to have probability 1 because something has to happen, if you remember our definition of probability spaces a while ago. By the same argument, if we're mapping points to an interval and all points get mapped to an interval, when we all points in the sample space, I mean all outcomes get mapped to our interval, when we consider like the probability of all the outcomes, maybe they could be here, that map to a certain point A, plus the probability of all the outcomes, maybe here, that map to a certain point B, and so on and so forth. When we add all of those guys up, they should add up to 1, okay, because these pre-images of each of them has to cover, like all of them together, their union cover the whole sample space, and as in the case of the discrete random variable, they also have to be disjoint because the function can only map to one of the values, right? Like the function cannot map to A and B simultaneously, like the same outcome. So again, let me come back to here and let me give you a little summary of where we are up to now. What we have said is we want to define continuous random variables. We're going to define them as functions that map to an interval of the real line or to the whole real line. It's the same idea. And now we're asking ourselves, what if I consider the set of points such that the probability that the random variable hits one of those points is non-zero? Well, the sum of those, by what I just said, has to add up to 1. So now we're going to see that there cannot be that many of those points if we want the sum to add up to 1. So what do I mean by that? So can S be a whole interval? We're going to see that it can actually not be the whole interval. And this has to do with the fact that uncountable sets are a bit weird. Okay, so let's consider, again, like I think I used blue. So let's consider this interval I, okay? And now I'm going to say, okay, like let me take all the points. Let me take all the points in I, remember this is the interval I, such that the probability that the random variable is equal to each of those points is between 1 over n and 1 over n minus 1. Okay, I do this for n equals 1, n equals 2, n equals 3, and so on and so forth. So for n equals 2, for example, I do this for n equals 2, 3, 4, and so on. N equals 2 is probabilities between 1/2 and 1. N equals 4 is, n equals 3 is probabilities between 1/3 and 1.5. N equals 4 is probabilities between 1/4 and 1/3, and so on and so forth. Okay? Because eventually 1 over n goes to 0, this is actually a countable, like A1, A2, no, actually we start at A2, sorry. A1 doesn't make any sense, right? Because this would be probabilities between 1 and infinity. I mean, probabilities cannot be larger than 1. So A2, A3, A4, and so on. As I take n to infinity, you can see that I'm basically covering every possible values of the probabilities because I'm taking increasingly small probabilities. So if I consider the limit from n equal 2 to infinity of the union of all these sets, I'm covering the whole interval as long as we assign probabilities to each of the points, okay? Actually, I shouldn't say I'm going to say S. So all the points that are assigned probabilities must be in one of these guys, okay? To see that, you see what probability the point has, and then you take n large enough so that it's smaller than that value, and that's the an that you're going to assign that point to. Okay, so you can put any point in S which are the points within the interval that get assigned non-zero probability, we can put it in one of these ANs. Okay, so why am I telling you this story? Where am I going to? Where am I going with this? Now, maybe you can tell me whether AN can have more than n elements. And if you think about a little bit about it, the probability of all the elements that end up in each of the AN cannot be more than 1, right? Because we know that the sum of all these possible all of these possible points of the interval that are assigned a probability, the sum of all of them cannot be more than 1. So in particular, the sum of the ones that end up in AN can also not be larger than 1. So this means, because their probabilities are at least 1 over n, that there cannot be more than n points in each of these AN, in each set AN. Okay? There cannot be more than n elements. So now we have that because S is equal to the union from n equal to infinity of the ANs. Okay, basically what have we done? We have taken the probabilities that are assigned to each of the points in S, which is the set of points that are assigned probabilities, and we have ordered them. And when we look at them, we realize that this is a union of like a countable union, right? Because we can count n, 2, 3, 4, 5, and so on. It's a countable union. And each of the sets within this union is finite. It has at most n elements, and definitely countable. So we have a countable union of countable sets. That means that the points to which we're assigning probability are a countable set. And this is problematic because the whole interval is uncountable. So this basically proves that if we want to assign non-zero probabilities to points within this interval, we can only choose a countable number of them. We're going to miss out a lot, right? Because it's an uncountable set, so there's going to be uncountable that we miss out. And this is due to the weirdness of real numbers, the weirdness of our uncountable sets. But what do we do about it, okay? Like, they're very weird mathematically and so on, but we need to do something about this. And what we're going to do about this is we're going to say, there's too many points in the real line. I cannot define a continuous random variable that lands on real values and assign non-zero probabilities to more than a countable set of real values, which defeats the purpose, right? Because if we do that, then we have a discrete random variable, because that's a discrete set that we're mapping onto. Okay, so that defeats the purpose of modeling these quantities as continuous, as real values. Instead, what we're going to do is we're going to assign non-zero probability to the random variable belonging to intervals as opposed to individual points. This will mean that, and we will see that with an example, that the individual points are actually going to have zero probability. So this is one of these things where the first time you see it, you're like, this is very strange. Like, I'm modeling a quantity and I'm saying that it has zero probability of being equal to any particular point. But then when you think a little bit more about it, it's not so strange. Like, imagine that you're modeling like the length of something, okay? The length of a stick. You're going to think of the length of interval of like pieces of the stick, right? If you just took a point of the stick, then the length would be 0. It's the same with time. You like look at the duration of something. What's the duration of a single point? It's also 0. Right? So we actually do this all the time when we model continuous quantities. Point-wise, when we measure them, because remember that the probability is a measure like weight, like length, like time, and so on. When we measure a single point, the measure is often 0. So in that sense, it's really not so weird. Okay, so after this somewhat esoteric explanation about why, I like the word esoteric today, of why we cannot assign probabilities to individual points, we're going to define continuous random variables so that we can assign probabilities to any interval. Okay, so what is a continuous random variable? It's again a function, exactly the same as with discrete random variables. It's a function that maps a sample space to the real numbers, and I'm gonna maybe draw a picture. Okay, so that's the sample space, and we have a function that maps to the real numbers. So I'm going to draw the real line. This is the real line. And now, for a random variable to be a valid continuous random variable, what we're going to require is that when we consider any interval whatsoever of the real line, if we look at the set of points in the sample space that map to that interval through our continuous random variable, okay, this is the continuous random variable, those are the points that map to the interval. So in this case, this would be E. Okay, this is A, B, the interval between these two arbitrary points A and B. And for any choice of A and B, I can define an interval, and then I can look at the outcomes in the sample space that map to that interval. We're going to require that the probability measure assign a probability to these outcomes, to that event, so that the probability that the random variable belongs to an interval is well defined. Again, this might look scary because you start worrying. You're saying, oh, so now I have to build this probability space so that all these pre-images that I have here are well defined. No, you actually do not have to do this, because we're going to estimate other quantities from data that directly will encode these probabilities. This is just a mathematical formulation, which is, again, it's good to know that it's there, but we're never going to actually build it explicitly unless we need to like prove something, or you're doing like very theoretical research. But even in theoretical research, you usually don't build these probability spaces explicitly. The point is that these probabilities, any of these probabilities are well defined. And if those probabilities are well defined, then we have a continuous random variable. If you want a fancy name to name functions like this that can be valid continuous random variables, they're called measurable. Okay, so let me remind you a little bit about notation. Usually we write deterministic random variables without a tilde on top, and those can have a specific value. Random variables have a tilde on top. That means that their values are uncertain. The way we talk about random variables is probabilistically. We don't say, oh, the random variable is between 1 and 4. What we say is the probability that the random variable belongs to the interval between 1 and 4 is 0.5. Notice that now I'm not saying the probability that it's equal to 2 or that it's equal to 3.4, because those probabilities are actually going to be 0 because of the reason that we explained before. So we again only talk about the probability that the random variables belong to intervals. Okay, so when we reason about random variables, we don't want to reason in the original sample space. Like for example, to explain this, I am going to have to refer again to the original sample space, but it's one of the last times that we will do it. So we have this original sample space, okay? And let's say, and we have the real line here. Now let's say that there's two intervals that I'm interested in. Okay, an interval here, I1, and an interval here, and they're disjoint. Actually, I'm going to use another color for I2. It can be purple. And I'm modeling this continuous quantity that can be on the real line, and I want to, I'm interested in the probability that of the union, basically, that the random variable, I'm going to use black, is either here or here. Okay, so I'm interested in the probability that A is in the union of I1 and I2. Okay, this is the more general case where we have n intervals. Okay, so the question here is, because these guys are disjoint, we might want to say, oh, that's just the probability that A is in the first interval plus the probability that A is in the second interval. And that would be very nice because it would make our lives very easy, because then we can just reason about individual intervals and then add up the probabilities. This is great. But we haven't, the way we have defined continuous random variables, it's not immediately obvious that this actually holds. Okay, it's not immediately obvious that that holds. So let's see why it holds. If we consider all the points that mapped to I1 in the original sample space, and we consider all the points that map to I2 from the original sample space, and this is the random variable that we're interested in that maps them, we realize now, and this is very similar to what we did for discrete random variables, that there cannot be points that are both in this event that map to I1 and this event that maps to I2, right? Because the same outcome cannot be mapped to two different values, and I1 and I2 are disjoint. So now, if these two events are disjoint, the probability that the random variable ends up here is just the probability of this guy. The probability that the random variable ends up here is the probability of this guy. So if I'm interested in the union of these two, it's also the union of these two pre-images, the events in the original sample space. And by the properties of probability measures, the probability measure of their union is just equal to the sum of their probabilities. This is very nice because once we have established this, we can forget, we can completely forget about the underlying probability space and just reason directly on the real line and say, oh, the probability at a random variable is equal to this interval or this other interval. We can just sum up the individual probabilities because the intervals are disjoint, and we have proved that that is okay. Okay, so let me just write the mathematics for the mathematical explanation, especially when we have n intervals. And if we have countably infinite intervals, the idea is exactly the same. This is very fancy notation, but it's exactly what I just said. What we say is, oh, what is the probability that A is equal to this union? It's just the probability that A is mapped to these guys. Okay, so we have to look at the probability of all the omegas such that A of omega maps to that union. That's just the union of these pre-images of all the events such that they are mapped to one of these guys, right? In this case, I1 and I2. So this would be, we're referring to these guys now here. When I put this -1, this -1 here just refers to the points that mapped to I1, I2, and so on. So now, as I just said, those guys are disjoint. So, the pre-image of the whole union is equal to the union of the pre-images. Basically, that says that if you look at all the points that are mapped to this union, it's just the union of the points that are mapped to each of the individual intervals. Okay, so we have this equality where we can just consider the union of all those sets that map to each of the intervals. And now those guys are disjoint by what I just said. So, boom, we can just add the probabilities by the properties of probability measures, and we have that the probability of the union is equal to the sum of the random variable being in each of the individual intervals. And that's amazing because now we don't have to worry about the underlying probability space anymore. Okay, so because of what I just said, we can consider any possible union of intervals on the real line when we're talking about random variables, and we can compute the probabilities based on the probabilities of individual intervals. We can also consider intersections, we can also consider complements, because those again are going to be unions or, those are also going to be intervals or unions of intervals. Any set that is a union, intersection, or complement of a countable number of intervals in the real lines is called a Borel set. They form a sigma algebra. This is not important. If you remember, a sigma algebra is just a collection that satisfies the conditions that we had when we were building a probability space, where If you had two sets in the collection, then the union also had to be in the collection. If you had a set in the collection, the complement also had to be in the collection, and then the whole sample space had to be in the collection. So a Borel set is a valid sigma algebra over the reals. In this case, the sample space would be the real numbers. It's not, this is not super important. The thing is that now we are characterizing random variables as being in intervals or in unions of the intervals or complements or intersections of intervals. So we're basically characterizing random variables in terms of whether they belong to Borel sets or not. So a question that you could have is, so what if I'm interested in a set that is not Borel? I cannot represent it as a countable union of intervals. And then it actually, I mean, that would be a good point, because you cannot define the way we're defining continuous random variables right now. The definition would not apply. You might see some very weird things if you try to compute their probabilities. The thing is that it's very difficult to come up with a set that is not a Borel set. You can do it, but usually the way you do it is you really have to work hard to explicitly define a set that is not Borel, and you probably will never encounter one. Definitely not when you're doing data science. Probably even if you're doing theoretical research, you will never encounter a non-Borel set. If you want to know more about this stuff, though, which is very interesting, you can look at any advanced book on measure theory. Anyways, the point is that most reasonable sets can be represented by most reasonable subsets of the real line can be represented in terms of unions of intervals. So we're in very good shape, basically. Okay, because we the way we have defined continuous random variables, the probability that the random variable belongs to any Borel set is well defined. Okay. Now the challenge is, okay, we have defined things mathematically, but now we actually need to operate with continuous random variables. We want to manipulate them. We cannot use the probability mass function because the probability of individual points is 0. So what do we do? And what we do is we introduce the cumulative distribution function. The cumulative distribution function is the probability that a random variable is smaller or equal to a value a. And the idea is that a can be any value on the real line, so automatically the cumulative distribution function tells you the probability that the random variable is smaller or equal to any possible value. Those are all intervals, so we're fine. I mean, this should be well defined based on our definition of continuous random variable. And as we will see, it's very useful to characterize the random variable. So let's think of what properties this function is going to have. We'll see a picture in a moment. What is the probability that, so if we take the limit from a to infinity of the probability that the random variable is smaller or equal to a, this is the probability that the random variable is smaller than any value in the real line, right? Because we're going to infinity, so basically this is just the probability of the real line. We can make this a little bit more precise, but that's the idea. So this is going to have to be equal to 1, right? Because the random variable is going to be mapped to some point in the real line. Okay, so that is equal to 1. What is the so this means basically that the way we have defined the CDF, it always needs to go to 1 when a goes to infinity. What about when a goes to minus infinity, when a becomes arbitrarily small? If a becomes arbitrarily small, that's the probability that the random variable is smaller than any possible number. That's going to be 1 minus the probability that the random variable is somewhere on the real line. That probability is equal to 1. So the probability that a random variable is arbitrarily small eventually is going to become 0. Okay, so this tells us that any cumulative distribution function goes from 0 to 1. If we have 2 points and b is greater than a, now we're going to see, whether the cumulative distribution function, and we'll see a picture in a moment, increases, decreases, etc. Can the value of the cumulative distribution function be smaller for b greater than a? Well, let's see. We have that f of AB is equal to the probability that the random variable is smaller than B, and f of A is equal to the probability that the random variable is smaller than A. But B is greater than A, right? So this is actually equal to the probability that A is in minus infinity to A plus, sorry, union AB, right? So what I'm saying is, maybe a picture is better. What I'm saying is, if we have a point A and a point B, the probability, f of B, I just want to change the color. F of B is the probability that I'm here. And f of A is the probability that I'm here. And I can express the probability of being, actually it's the other color, right? The probability of being smaller than B as the probability of being smaller than A plus the probability of being between A and B. I feel that I made that explanation much more complicated than it needs to be, but that's the point. Okay, so we can actually separate A smaller than B into A smaller than A and A being between A and B. So this probability is equal to f of A plus the probability that A is between A and B, which is non-zero. So f of B, if B is greater than A, can never be smaller than f of A. Okay, hopefully that was clear. I think that wasn't my best explanation, but let's move on. So cumulative distribution functions in general are going to look like that. Like if you go to a small enough value, they're going to be equal to 0. And if you go to a large enough value, they're going to be equal to 1. And in the middle, they're never decreasing. They can never decrease. They can stay the same. That's fine. But they can never decrease. Okay, because of what we just said. Okay, so now we've said that the whole point of how we had defined continuous random variables is that we can define the probability of an interval. So now let's see if we can derive the probability of an interval in terms of the cumulative distribution function, because then we just need to define the cumulative distribution function. With that, we can find the probabilities that the continuous random variable is in any interval, and we can just work with that. Okay, that's the idea. So what's the probability that P is between A and B? So if we look at the probability that A is between A and B, I realize that I use often squiggly A for the random variable and then A without the squiggly on top for a value because I usually just run out of letters to use. So I'm sorry about that. Hopefully it's obvious from the context when I'm referring to a random variable and when I'm referring to the specific value. It should be clear when I write, right? Because everything with a squiggly line on top is a random variable, and everything that does not have a squiggly line on top is not a random variable. But I realize that when I talk, it becomes a little bit confusing. So sorry about that. But anyway, so here I'm interested in the probability that A, the random variable A, is between A and B. And my strategy is going to say the same as before, essentially. I'm going to say, the probability that A is smaller or equal to, squiggly A is smaller or equal to A, plus the probability that A is between A and B, that basically covers the probability that squiggly A is smaller or equal to B. Okay, so this probability is actually the probability that A is in this union of intervals. The intervals are disjoint, So we have that this guy is just the sum. This guy is just the sum that that A is between A and B, and A is more or equal to A. Squiggly A is more equal to A. Anyways, I can now express the probability of the interval as the value of the CDF at B minus the CDF at A. So let's take a look at the picture. Imagine that I want to know the probability that the random variable is between 0.5 and 2.5. So what's the probability that the random variable is here? Very easy. I just look at the value of the CDF at 2.5. I look at the value of the CDF at 0.5, and I subtract. I take the value of CDF at 2.5 minus the value of the CDF at 0.5. That gives me the probability that the random variable is in that interval. Okay, now let's look at another example of, in this case, the probability, I forget what it was. I think the probability might be 0.5 in this case, but I don't remember. No, maybe it's a little bit less. Okay, maybe I should have put the value there. It doesn't matter. Okay, so this is an example of another CDF. It goes from 0 to 1. And the interesting thing is that it's linear. Okay, this line here, the value of the CDF is linear. So now let's take a look at what the probability is that the random variable is in some interval here. Okay, this is the value of the CDF. What's the value that the random what's the probability that the random variable is below 0? Well, you're gonna, if you want the probability of any interval below 0 and the CDF has the same values, you're going to subtract those values to find the probability, so that probability is going to be 0. So we realize that anywhere where the CDF is flat, any of those intervals are going to have probability 0, essentially because the probability that the random variable is here and here is the same. So then that means that the probability that it's in this interval is 0. So in this case, we very quickly see that the random variable can only be between 0 and 1, because that's where the CDF is not flat. And between 0 and 1, the value is u, okay, where u goes from 0 to 1. So we want to look at the probability of each interval. This is going to be f of b minus f of a. And f of, like, the CDF at b is equal to b, the CDF at a is equal to a, just because of this definition. So when something interesting that happens when the CDF is linear is that the probability of belonging to an interval is proportional to the length of that interval. And if you think about it, this captures the notion of some quantity being kind of uniformly distributed, right? Like maybe, you know, I take like a stick and I choose a point at random. The probability that I'm going to end up in an interval intuitively should be proportional to the length of the interval, right? And we can see here that that is achieved by having a linear CDF. Okay, so here, what is the probability of being at exactly 1 point? Well, at exactly 1 point, if the CDF is continuous, basically the probability that u is equal to u is going to be f of u minus f of u. If I want to get fancy, I could say, you know, the limit when epsilon goes to 0 of f of u minus epsilon. But it doesn't matter because here it's obvious that the CDF is continuous. So every time we have a continuous CDF, if we look at the probability of an individual point, what happens is that it's just equal to 0, because this is just equal to 0. And this captures this notion that we had said before, that when we're trying to assign probabilities to continuous values, the value of an individual point is going to be 0. And this is definitely the case for this CDF or for any CDF that is continuous. Again, that's not very problematic, right? Because if you're measuring a certain quantity at like an unbelievably high accuracy, okay, I measure like a distance and it's going to be, you know, up to like the 12th decimal point. if I think of the probability that I'm going to end up in any point, it's actually going to be 0, right? Like in the limit where I consider an arbitrarily high accuracy, because no way I'm going to, land on exactly that individual point. So hopefully that gives you some of the intuition. Okay, so we have defined the CDF that goes from 0 to 1. It's nice because it gives us the probability that the random variable is in any interval. There are other useful quantities that are connected to the CDF, which are called quantiles. So quantiles are the n quantiles of a distribution or of a continuous random variable are n minus 1 point that cut up the real line. Okay, so we have the real line. I'm going to draw it here. This is the real line. And now the quantiles cut up the real line. So Q1, Q2. I'm just going to do the 4 quantiles, okay? So there's always n minus 1. So if we're considering the 4 quantiles, there's going to be 3 of them. And the idea is now the probability that the random variable is here is going to be equal to 1/4. The probability that the random variable is here is going to be equal to 1/4. The probability that the random variable is going to be equal to 1/4. And the probability that the random variable is here, no surprise, I guess. I'm trying to look for another color. This one is going to be 1/4. So basically the quantiles separate the real line into pieces, and each piece has the same probability, or more precisely, the probability that the random variable is inside any of those pieces is going to be the same. If we consider 4 quartiles, we cut up the real line into 4. If it's deciles, we cut it into 10, and so on and so forth. I mean, you can consider another popular choice is 100. Then you get percentiles. You might have heard about percentiles. Okay, so an important quantile, well, actually, before I get into that, if you realize here, the probability has to be 1 over n. Here, now we have 2 quantiles, the probability has to be 2 over n. Here, the probability is 3 over n. So another way of defining quantiles is for what values of at the quantiles, the CDF is equal to 1 over n, 2 over n, 3 over n, and so on. Okay, that's another way of defining quantiles. And what I was going to say earlier is that the quantile in the middle that separates the real line into 2 segments such that the random variable has a probability 1/2 to be in either of those segments, that is called the median. Okay, that is called the median. I missed that, by the way, to tell you that the 4 quantiles are called quartiles, the ones I was talking about before, Q1, Q2, Q3, Q4, and we often use a capital letter for those. That's not very important. Well, actually, I've made a mistake here, if you realize, because there's only 4 quartiles, right? Q4 doesn't make any sense because we cut up into 4 pieces. There's only 3 cut points. So as I was saying, the cut point in the middle that separates the real line into 2 segments such that the random variable has a probability 1/2 of being in either segment is called the median. You might have heard of it. And it's defined like this. Or equivalently, it's the point where if I plug it into the CDF, I will get 1/2. So let me show you a picture. Here I'm focusing again on the 4 quantiles. So there's 3 of them. If I want to find a point such that below it there's 1/4 of the probability, then I look at the point where the CDF is equal to 1/4, and that is the first quartile. Okay, remember that the 4 quantiles are called quartiles. If I want the median, I look at the point where the CDF is 0.5, and if I want the third quartile, I look at the point where the probability is equal to 3/4. The CDF is equal to 3/4. For this other more exotic CDF, same thing. Where is the CDF equal to 1/4? Here. Sometimes when the CDF is flat, like for example here, you could have several values that are mapped to the same CDF value. So all of these guys where the CDF is flat could potentially be the median. Here we have just taken the midpoint as the median. It doesn't really matter very much what you do there. And finally, if you want the third quantile, you go to 3/4. Okay, so now we have shown that the CDF is super useful because it tells you the probability that a continuous random variable is in any possible interval. So it actually provides you with enough information to describe the continuous random variable completely. And also it gives you the quantiles, which is a quick way of figuring out where the probabilities are distributed. So that's kind of nice. Now, how do we estimate this from data? Well, we do what we always do, or at least up until now, which is we look at the definition of the CDF and we realize that it's a probability. And when we see a probability and we want to estimate it with data, what do? We use empirical probabilities. Okay, so that's what we're going to do. We define the empirical cumulative distribution function, the empirical CDF, as the fraction of points that are below any value that we could plug in there. Okay, so if we want to know the empirical CDF at, let's say, a = 5, we look at our data set, we count all the points that are below 5, and we see what fraction they are of the total. Okay, n is the total number of points. So essentially the empirical probability that is below 5. Sorry, that the data are below 5. Because of that, the empirical CDF is going to be always piecewise constant, right? Because if I look at the empirical probability that I am below 5 here, for example, these are the data points. So here, this is a ROC plot, it's called, of the individual data points that I have observed. This is some GDP per capita data. We'll talk about it in a moment. Every time, if I'm considering the probability of the empirical probability of 5, then I look at how many points are here. What's the fraction with respect to the total number of points? And in this case, it's about like 0.46. That is not going to change until I encounter another point. So here I've encountered another point, so the probability is slightly higher, 1/n higher, in fact. Okay, so this thing is just going up 1/n and so on. Okay, by 1/n, by steps of 1/n every time there is a data point. So the empirical CDF is going to be actually piecewise constant always because of the way we have defined it. If you want to estimate the quantiles, you do something extremely similar. The quantiles of the continuous distribution just cut up the distribution into pieces such that the probability that the random variable was in each of those pieces was the same. Here, essentially the empirical probabilities are going to be the same. So the empirical probabilities that you're below the first quartile is 1/4 if you're looking at 4 quantiles, at quartiles. The empirical probability that you're below the empirical median, or sometimes called the sample median, is going to be 1/2, and so on and so forth. You can also just use the empirical CDF directly. So here I've plotted the empirical CDF of the heights of 4,000 soldiers in the US Army, or 4,000 people in the US Army. I'm not completely sure if they're soldiers, all of them. Okay, and you can see that the empirical CDF goes from 0 to 1, because eventually, you have a fraction. The fraction can only go up to 1, and it will go up to 1 when you make the heights large enough. And you don't see here that it's piecewise constant because there's so many numbers, but it is, you can believe me. And now if I want to know, the first quartile, then I look at the value where the empirical CDF is equal to 0.25, which is here. And that means that 1/4 of the soldiers have height less than this value. Then another 1/4 are in here, between the first quartile and the median. And another 1/4 are here, between the median and the third quartile, and then the rest are here. Okay, so very quickly we see how the heights are distributed. If you want to see it even quicker, what you can do is you can plot only the median and the quartiles, and usually this is called a box plot. It was invented by Tukey, and the idea is you want to visualize very quickly how this data set is distributed, and what you do is you plot the median, the first quartile, the third quartile, and then you plot these things called whiskers, which are equal to 1.5 the interquartile range. The interquartile range is just the difference between the third and the first quartile. And then if there's any points left after 1.5 times the interquartile range, then you just plot them as outliers, and this enables you to see if there are any data points that are particularly large or particularly small. In this case, these people are very tall and these people are pretty short. Let's take a look at the same thing for another data set. So in this data set that we saw here, things are quite balanced, right? You can see that the difference between the third quartile and the median, the first quartile and the median is kind of almost the same. Not a lot of outliers, you know, like it's a very symmetric data set. This is a data set of the GDP per capita of countries in the world in 2019. Okay, so again, look at the this is the empirical CDF. It goes from 0 to 1, and we can now see where the first quartile, the median, and the third quartile are. And this might be surprising, right? Because it means that 1/4 of all the countries are here, another 1/4 of all the countries are here, another 1/4 of all the countries are here, and then 1/4 of the countries are actually here. And here it's still going up. You can see it, or here. I believe that this is Monaco or Liechtenstein. So there are some countries that have massive GDPs per capita, but most countries have really small GDPs per capita. GDP is gross domestic product. It's just a macroeconomic quantity that quantifies economic activity in the country. Okay, so this data set, if we look at its box plot, the box plot actually immediately tells us that it's really squashed, like that most countries are here. It also tells us that, you know, there are some countries here, and it shows us these spectacular outliers. I think that's Monaco and Liechtenstein, and that there are these other countries that are also really high. Okay, so by just eyeing the box plot, we immediately see how the data are distributed very quickly. So I really recommend that you use this when you're doing data visualization. It's really useful. As another example of how useful the box plots are, here are box plots of the temperatures in Oxford in each month over the last 100 years. And we can see very quickly that things are, you know, warmer in the summer, things are colder in the winter, and we can also see that the temperatures change more in the winter than in the fall or in the spring. Okay, just by eyeballing it. And we can see, you know, that sometimes there are outliers. In particular, February can be extremely cold. And August can be, you know, there are more outliers in August maybe. Very quickly we see, for example, that July is actually warmer than August, which I was surprised about. Okay, so box plots are really useful to visualize how data are distributed within a data set really quickly, and also to compare data sets. So what have we learned? We have learned the mathematical definition of continuous random variables. The important thing was that we cannot talk about the probability of the continuous random variable being equal to each point, because that's going to be 0. We instead have to reason with intervals. The cumulative distribution function encodes the probability that the random variable is in each interval. We just basically have to subtract the CDF at different points to get the probabilities of intervals. It's directly connected to quantiles that cut up the real line into regions with the same probability. And we also saw how to estimate both the cumulative distribution function and quantiles from real data. Thank you very much.